Okay, good morning. So, we start today's lesson. I want to introduce you a piece of notation, which is the factorial of a non-negative integer. But to introduce you why we need this, I'm just going a little bit ahead, because the next lesson will be the permutation according to the book. And in those cases, we have the product of consecutive integers appearing a lot. So we just invent a new piece of notation to be able to write those things more compactly. For example, if I ask you in how many ways 10 people can stand in a queue, of course we know that in a queue order matters. So if I want to see, I give you 10 people and then you want to set up a queue for getting something. And then this means that this is a very simple problem, by the way. You should be able to solve it immediately. In how many ways I can arrange 10 people in a line so that order between people matters. So how can we do that? This task is a 10-stage task. So I would say that, okay, in a queue line with 10 openings, I just say that the first opening or the first position can be occupied with any one of those 10 people. Yes. And then after the first stage is done in any way with one of those people, the next position in the queue can be filled up with 9, and the next position will be filled up with 8, and the next position up to, 3, 2, 1. The answer is this one. So there are two ways. Either you have your calculator with you and multiply this, or then you have to write this all the time like this. So these kinds of products that are consecutive, this is the product of consecutive integers, appear from now on quite a lot, or frequently, would say. So let us invent a new notation for that so that we can make it more compactly. So this is, in this notation, is simply written as 10. We put an exclamation mark in front and read it factorial of 10 or 10 factorial. Okay, so that is it. It's just a piece of notation. But of course, whenever we introduce some notations, it is better to go a little bit around that to understand the notation better. So this would be our lesson today. So that I will introduce this notation formally and give you some examples around it, and the lesson will be finished. Okay, so let us go to these slides here. So let n be a non-negative integer. So first of all, there is no negative factorial. Of course, at the university level, sometimes they talk about negative factorials, but for you, we do not have -5 factorial or something like that. N should be a non-negative integer. It means that n is either 0, 1, 2, 3, 4, etc., etc. The factorial of n is denoted by this symbol, n exclamation mark, and it is defined as follows. If n is 0, the answer is just simply 1. This is definition, okay? And if n is 1, the answer is again 1. But if n is an integer greater than or equal to 2, you start from that number and then multiply that number by its previous number, multiplied by its previous number until you reach to 1, and then you stop. That's it. Is that clear? Okay, so remember, by convention or by definition, 0 factorial is 1. It's the reason for that we will see a little bit later, so that's a good convention later. So 0 factorial is actually equal to 1. 1 factorial is also equal to 1. And then if I ask you what is 2 factorial, you will tell me I start from 2 and multiply it by the previous number, and I repeat this process until I reach to 1, then I stop and calculate the product. So the product here becomes 2. So coincidentally, 2 factorial is also equal to 2. But if I go to 3 factorial, it means 3 times the previous, and when I reach to 1, I stop and calculate the product. So it becomes 6. So 3 factorial is 6. And then if I ask you what is 4 factorial, that's the same thing. So 4 times 3 times 2 times 1, which of course you can just multiply 4 by the previous factorial, yes? Because we have already calculated that part. So this becomes 24. And factorial also grows rapidly. Not as strong as powers, but it also grows rapidly, okay? So for example, let us calculate some of them. 5 factorial, you already know. It is 5 times 4 factorial, yes? Or if you want, you can write this. And then the answer is 120. And 6 factorial is 6 times 5 times 4 times 3 times 2 times 1, 720. Let me also write 7 factorial as that example. Instead of writing it from scratch again, I know that, is it sensible for you if I write this? Yes? So 7 factorial means 7 multiplied by the previous factorial. So if you multiply this by that, it becomes 5040. So you see that increase is more or less rapid, but not as exponents, power functions. Any questions? That's very simple. And this I want you to learn. This remark is this. It's, by the way, very obvious. If you have a factorial of a number, sometimes you have to break it down. Okay. So if I ask you what is the factorial of n, you can say n itself multiplied by the previous factorial. Yes. For example, 30 factorial sometimes is needed. You break it down. So if you want to, you can write it as 30 times 29 factorial. Or if you want, you can break it more. You can write 30 times 29, but times 28 factorial. Even if you want to break it more, you can write 30 times 29 times 28, and then times 27 factorial. So you need to be flexible according to what you need. You might need to break the factorial into more pieces. But there is nothing very strange about that. Yes, please.
What would happen if we broke it down all the way to 0 factorial? Can we go any further beyond that?
No, because you can in principle, but this is not part of your lesson. So negative factorials need a concept of gamma functions, which we'll not study. And by the way, they do not appear in combinatorics. So those negative factorials appear somewhere else, not in combinatorics. Okay, yes, please.
All factorials.
Pardon?
Is all factorials even?
Yes, yes, because after that stage, yes, there is a 2 involved. Okay, so now let us see. Yeah, these kinds of simplifications I want you to be able to do. And please do not invent new rules, yes? So 5 factorial plus 2 factorial means you need to know 5 factorial, you need to know 2 factorial, and then add them up. Okay? And then I have compared them together because sometimes I have seen people make this mistake, 5 factorial plus 2 factorial, they just simply write 7 factorial. But that's not correct, yes? So let us just try to check them out. So for example, if I ask you what is 5 factorial plus 2 factorial, the answer is what? 5 factorial is on the board, you have to calculate that. So if you want, you can write it 5 times 4 times 3 times 2 times 1. Whatever it is, you add it. 2 factorial is 2 times 1. So this becomes 120 plus 2, which is 122. And it has nothing to do with 7 factorial. So if you want to calculate this, what is this pair of brackets gives the priority to addition operation. So this means that I have to first calculate this, which becomes 7, and then factorial it, yes? So this becomes, as we did before, is 5,400. That's 40, and then these two numbers are quite different. Okay, so these type of questions, we need that property that I mentioned. Sometimes these kind of things appear a lot in combinatorics, as we will see later. So I want you to understand this breaking rule to be able to simplify them, yes? So for example, number 3, if I want to solve it on the board, so what is your suggestion for me if I want to simplify that? Of course, you can calculate 12 factorial, which by the way is quite a big number because you need to multiply this by 8 and then multiply it by 9, by 10, by 11, by 12, and then it becomes 12 factorial. Okay, so what should I do?
You can rewrite 12 factorial as 12 times 11 times 10.
Yeah, exactly. So I can break it up until I need. So I just I can do it. So I would write 12. I can stop here and write 11 factorial, but that is not that useful because nothing can be simplified, yes? So this motivates me, no, you need to continue. So 11 times 10, but then I stop with writing 9 factorial, yes? And then I divide by 9 factorial. Then I would say, okay, whatever 9 factorial is, I don't care because now it is simple. Cancelled out. And then I will get this number, I think 1320, yes? Okay, but I mean, if I didn't want to simplify this, it would be actually a very hard problem. Okay, so let me write the other one on the board and wait for you. It's very simple. So the other problem is 13 factorial divided by 10 factorial. When I write them like this, I mean they are multiplied. Yes? So, okay, so please calculate that. So what is the answer? Yes, is that clear? So how should I do that? I need to break down these 13 factorials, yes? So it becomes what? 13 multiplied by the previous number, but it is not enough if I stop there. So I will continue one more step, and then I multiply by 10 factorial because my goal is to get rid of the denominators as fast as I can. Yes, but I do not need to open 10 factorial because whatever it is, I don't care, it will be cancelled with that one. So I copy and paste 10 factorial part, but 3 factorial I have to write it down. There is no way. So 3 times 2 times 1 is 3 factorial. And then of course these 10 factorial and that one are cancelled. 3 times 2 is 6. 6 and 12 are also cancelled. So it is 2 times, yes. And then it becomes 286. Just multiply. Okay. Another type of questions that you might need is that I give you a product of some consecutive integers, and it is good to remember how can I write it in factorial form. That you need to know the question in both directions. Sometimes you need to simplify a factorial to a number. Sometimes you already have a product of numbers you want to write as using the factorial symbol. So 10 times 9 times 8 times 7, I want to write it as the quotient of 2 factorials, and that's also very simple. Yes. I hope that is clear for you. This is not 10 factorial, yes? So how should I write that one? So I have 10 times 9 times 8 times 7. I want to write it as I want to use factorial symbol to write this expression. Yes, so what should I do? For having factorial, I need to have the product all the way up to 1. Yes? So this motivates me to multiply what I need and I don't have, meaning 6 times what? 6 times 5 up to 3 times 2 times 1. And by the way, this dot doesn't make sense here because there's only 1 left. Yes, and then 4. And then I multiply this myself. I'm not allowed to change my problem, so to compensate for that change, I have to divide by the same expression, yes? Is that right? Yes, 6 is also. Okay, so if I ask you what is this, you would say this is completely cancelled with that one. I am left with exactly what I had. So, but now you see that it starts from 10 and goes up to all the way up to 1, which means it is 10 factorial. And the denominator starts from 6 and goes up all the way up to 1, so it is 6 factorial. Yes, that's it. So this product, if you insist to write it in factorial form, you should write it as 10 factorial over 6 factorial. Yes, is that right? Okay, so let us solve a little bit more interesting problems, yes? So, number 7. So n is an integer bigger than 1. We want to show that this is true. Okay, I want to wait a little bit for you. So this tells you that whatever n is, n factorial is equal to this combination. Okay, I want to wait a little bit for you. Okay, could you do it? Yes or no? Not yet. Okay, so this also, so this is mathematics, so it has always surprises for you. Even though this is simple, might be sometimes it is confusing. No, but it shouldn't be hard. Let us see what is going wrong here actually. Of course, I want to prove that this is true, so I have n factorial on the left-hand side, and then I have n minus 1 factorial multiplied by n minus 1 factorial plus n minus 2 factorial. Yes, we want to show that for any integer greater than 1, the left-hand side is equal to the right-hand side. Yes.
Just n minus 1.
Yes, thank you. Thanks. Okay, so what we do, I will start from the right-hand side because it is not very clear. Usually when you want to prove identities, it is better to start from the complicated side and try to simplify it as much as you can, yes? So what is your suggestion for me? You have to do something, yes? So from left-hand side, so from right-hand side, I start. So what, do you have anything to say? Yes?
On the one in the brackets, you can factor out n minus 2 factorial and get n minus 1 plus 1.
Yeah, okay. So, but before that, you have to break it down, yes? So if everyone is supposed to understand. So what you are suggesting is that to break this down, yes? How should I break this down? The rule was clear. If I give you a number factorial, if you want, you can write n itself, but multiply it by the previous number factorial. That's the same rule. So, but my starting point is n minus 1 itself. So I write n minus 1 and multiply it by the previous integer's factorial. So what's that?
n minus 2.
The previous integer is n minus 2, yes? So it means that it is n minus 2 factorial, yes? By why this is useful, it's better than doing nothing, yes? And this is a little bit promising because at least you see that I have a product of two numbers here, and this number exactly repeats itself here. So I can factor this out. That's just a number, so I take this number out. N minus 1 is already there. I pull this out, n minus 2 factorial is here now, and then what is left? N minus 1 from this one is left, plus, what is left here? 1. Yes. And then suddenly you see that the problem becomes simple, yes? Because these two are gone. What I need to do is to arrange the order, of course, if I want to understand it better. This is the product of three numbers. One of them n minus 1, the other one n minus 2 factorial, and the other one n. So let me write n first, and then n minus 1, and then n minus 2 factorial. I hope that you immediately understand this is the same as n factorial, yes? Because n minus 2 factorial starts from 1 times 2 times 3 up to this point. What is the integer after n minus 2 is exactly n minus 1. What is the integer after n minus 1 is exactly n. So if I ask you what do you see, you would tell me that I see the product of all integers from 1 up to n. And that is exactly the meaning of n factorial. Yes? So that is equal to the left-hand side. Right-hand side. Yes? Is that clear? Good. So let us go back to slides. And then still I want you to solve that one for me. Use mathematical induction, or otherwise show that for all natural numbers, 1 times 1 factorial plus 2 times 2 factorial plus up to n times n factorial is n plus 1 totally factorial, but minus 1. So we want to prove that, yes? Okay, I want to wait for you, okay? Okay. Let us solve it. So could you solve the problem? Yes, I don't think it's hard if you use mathematical induction, but I have written otherwise. you have to be creative to find another way to solve the problem. It would be easier than using mathematical induction, but you need to be more creative. I will also teach you how to do that for this particular case. It's not always possible. So the first thing is to write P of 1 and make sure that P of 1 is true. So P of 1, you give me n, I have to start the process from the first term and up to when I reach to this number that you gave me. But when you gave me 1, when I start, I also finish, yes? So the left-hand side is 1 times 1 factorial. And then the left side. And the right side becomes 1 plus 1 totally factorial minus 1. But I need to see if this is true or false. It is clear. 1 factorial is 1 times 1. So this is just 1. This is 2 factorial, which is 2, but minus 1 is again 1. So it's true. Then we assume that this is true for P of k, so it is true for k, so this means that I just need to copy and paste this and change into k everywhere, yes? So assume to be true. And then I need to prove the next step, which is the k plus first step. So it means, and you have enough experience, yeah? So 1 times 1 factorial plus 2 times 2 factorial. In principle, I should go up to k plus first step, which means k plus 1 times k plus 1 factorial. But by the experience you gained so far when we were dealing with this, you know that it is always good to write the previous step in these ones containing these dots, yes? So this is the left-hand side, and the right-hand side I change into k plus 1, which becomes k plus 2 factorial minus 1. So to be proven, yes? Okay, so again, I start from the left-hand side of what I want to show. This is guaranteed by the assumption. So I will start from the left-hand side, and you know what to do, yes? Because the hard part of this, we know what is the answer based on my assumption, yes? The left side is the whole thing, but from the first one up to the kth one, I know the sum is equal to that. Very simple exercise. So k plus 1 factorial minus 1. And then there is one extra term involved here. So I have to add it. So it's k plus 1 times k plus 1 factorial. So the only thing I have to do, I have to simplify this. But there is no, by the way, simplification at all, yes? Because you need to have an eye on what you are supposed to prove. You are supposed to reach to this expression. You need minus 1, but you already have your minus 1. That's good. So I put minus 1 here because I need it. But then there are 2 terms involved, this one and that one. So what do you suggest here? What should I do between these two?
About k factorial.
Yeah, k plus 1 factorial repeats itself here. So let us pull it out, yes? So this becomes k plus 1 factorial. And then what is left from this one? I pull this out, it means I divide it, it becomes 1. And then I have plus sign. I pull this out, so k plus 1 is left. That's it. And then I start simplification a little bit. So 1 plus k plus 1 has a better name, and that is k plus 2. And if you don't mind, let me write k plus 2 on the left side. So this becomes k plus 2 multiplied by k plus 1 factorial. So this should be, you should be comfortable with this conclusion. Immediately you should detect a pattern. You have factorial of a number multiplied by the next number, yes? So k plus 1, whatever it is, k plus 2 is the next number. So this, whenever this happens, it means that you can combine them into 1 factorial, because this means from 1 multiplied up to this point, and then you are multiplying by 1 more number. So I hope that you agree that I can write k plus 2 factorial minus 1, yes? And that's it. And that's exactly what I want to show, which is the right-hand side, so it is proven. But it is also instructive if we see that these kinds of sums somehow these kinds of sums somehow gives rise to some kind of telescopic sum. These are famous kind of sums, but sometimes you have to be creative, and this is not always possible, and rarely possible. Yes. So, but in this case, it is possible. So let me also teach you that. For example, if I give you m. I want to understand how can I write this. So m is a positive, let me take m to be a natural number, any number that you like. I want to change the form of this term. Okay, so how should I do that? I will do this. This is why I'm saying that you have to have experience if you want to do it in that way. And as I told you, this is not always possible. So instead of m, I write m plus 1 minus 1. And then I multiply it by the same m factorial, yes? And then I do like this. I multiply this here minus multiply this here. So this becomes m plus 1 multiplied by m factorial. You might say why I'm doing these weird things. Because I know what I'm going to do. Yes, I had solved so many of these kinds of problems, but these are not easy to detect. So you need to follow me that I am not telling a lie to you, yes? That's the only thing that you can do. So do you agree with this one so far? But then you can immediately, this I expect you to be able to detect this pattern. What can I write instead of that? N plus 1 factorial. And then what I gain from this kind of weird calculations, I realize that if you give me m, the combination m times n factorial can also be viewed as a difference. M plus 1 factorial minus m factorial. Okay, so this is on its own an exercise. So here I have a product, but here I have a difference. So I showed you this kind of product can also be written as a difference. Yes, that is what I showed here. But you might ask why this is useful, because then I use this for each one of those terms, yes? So let me bring this down a little bit. So you see here, every term in this sum has exactly this form. It is a number multiplied by that number itself factorial. So what does it mean? It means that if I give you 1 times 1 factorial, you can write it as 2 factorial minus 1 factorial. Do you agree? Because here, I am giving the role of m to 1. So this becomes 1 times 1 factorial, but 1 plus 1 is 2, so 2 factorial minus 1 factorial, yes? So I was able to write this product as a difference. I can do the same thing for the next term. The next term is what? 2 times 2 factorial. What can I write for it?
3 factorial minus
3 factorial minus
2 factorial.
2 factorial, yes? I haven't written this next term, but let me just try to understand that. So this is 3 times 3 factorial. What can I write? I can write 4 factorial minus
3 factorial.
3 factorial, yes? And if I continue this list, somewhere I reach to n minus 1 times n minus 1 factorial, and the next term will be n times n factorial. But again, to understand the problem better, what can I write for n minus 1 times n minus 1 factorial? I can write what?
N factorial
N factorial
minus n minus 1.
minus n minus 1 factorial. And then finally the last term becomes n plus 1 factorial minus n factorial. Yes? I'm just trying to teach you this. You don't really need to understand that. But this is something like a telescope, yes? Because I want to calculate the left-hand side. It is a sum. So this motivates me add the left-hand sides. But equivalently, I can also add the right-hand sides because each term on the left is equal to each term on the right. So if I do that, what happens? If I add them up, the left-hand side is exactly what I want to calculate. Yes? So it becomes 1 times 1 factorial plus 2 times 2 factorial up to n times n factorial. But this is acting like a telescope, yes? Do you know the telescope, yes? So what is happening, if I add them, this term will be cancelled with this term. And then this term will be cancelled with this term. And then exactly the same thing, this will be cancelled with that one. When I start continuing this, this will be cancelled with the previous one, and this will be cancelled with that one. So it means that all these terms are cancelled except two. One the very first and one the very last. So it becomes n plus 1 factorial minus 1 factorial, yes? So this becomes n plus 1 factorial minus 1 factorial, but 1 factorial is simply just 1. So this way is superior to mathematical induction. Why? But of course you have to be creative, yes?
It's faster.
It was not that faster, yes? Especially if you want to think about it. No, this is superior because I gained the result. But in mathematical induction, the weakness of mathematical induction is always with you. They have to present the correct formula, then you can prove it. But here, even if I didn't know the answer, I was able to get the answer myself. That's the difference, yes? Okay. Let us go now to the next question. Let us see what we have here. I think these questions are actually good. And these two questions, I will add one probably if you have time to it. So I want to wait for you again. This is somehow, I'm asking you determine n if n is a natural number and n factorial is this weird combination. I want you to understand what n is. It's solving an equation. N is unknown. You want to find n. And this example, this is a more interesting one. If S is this sum of factorials, determine the units, it should be units, the units digit of S squared. So it's somehow number theory. Yes? So I want you to think about it. By the way, this is the nature of discrete mathematics. There is no way that I can teach you what to do. I can just bring you a diversity of examples to draw your attention to the different possibilities. Yes. Okay, we solved this one, and I think I will add one or more example today, and then we are done. Okay, do you have any idea for this simpler question? Assume that you don't have access to the calculator, of course. So n factorial is supposed to be equal to 8th power of 2 multiplied by 3 to 4, 5 to 2 times 7. So what is the strategy? Yes?
I started by, considering that n factorial is n times n minus 1, times everything. So I started by finding or pulling out a 2 from the 2 to the power of 8, and then I looked, there was already a 3, and then I pulled out a 4 from 2 to the
Yeah, exactly. So you want to start, instead of starting from the left, you start from the right and try to organize it as a product of 1, 2, 3, 4 up to some point which we don't know. Yes? So this is exactly this reverse engineering one. So of course the right hand side is equal to, okay, I need a 2. So how many 2's I borrowed? I borrowed 1, 2 and put it here. 7 2's are left. So let us try to understand that. So far I have 7 2's left. But then I need 3. So I need to borrow 1 3 and put it here. So far I have 3 3's left. And then after that, after 3 I need 4. But 4 consumes 2 2's, yes? So I had already 7 2's. I need 2 of them, because when I say 4, it means 2 times 2. I had 2 to the power 7. I borrowed 2 of them. So 5 of them are left. So when I write 4, I consume 2 more 2's here, yes? And then after that is 5. Do I have enough 5's? Yes, I had 2. Now this is gone, 1 is left. Okay, and then I want to go to 6. But what is 6? 6 consists of 2 multiplied by 3 So do I have 2? Yes, I had 5 of them. I borrow 1, it becomes 4. I need 1, 3, so there are 2 left. So when I write 6, this is the price that I have to pay. I need to borrow 1 more 2, 1, 3, I put them here. And then after 6, I have 7. Unfortunately, I have 1 7 only, so 7 is gone. But what is 8? 8 is 2 to the power 3, so it consumes 2 3s. Do I have enough? Yes, still I have enough. 1 is left. And then I have 9. 9 consumes 2 3s, and exactly I have 2 3s, so finally I got rid of 3s. And then I have 10. What is left? You see, 1 2 is left, 1 5 is left, and that's exactly 10. So I consumed everything, and then I am done. So this means that what is this number now? Which factorial is that? Of course, it doesn't matter if I put 1 here or not. Multiplying by 1 doesn't change anything. And if you see, it is just 10 factorial. So this answer is n equals to 10. Yes? It was simple. But now let us go to the next problem. A number of the sum of 19 factorials in this way is given, and then you are supposed to determine the units digit of s squared, not s itself. But this is number theory. Whenever you want to find the units digit, do you remember from number theory what we are supposed to do? Yes?
Modulo of 10.
Modulo of 10. Because modulo of 10 gives me the remainder by 10, but remainder by 10 is also the units digit. Yes? So this means that I need to ask myself this question. So s is actually 1 factorial plus 2 factorial plus 3 factorial and then up to 19 factorial. I need to ask myself, what is S2 in module 10? Yes? Of course, that question mark, there are infinitely many answers, but I need the numbers from 0 up to 9, yes? So I have to adjust it if it's bigger than that. But of course, if I want to answer the question mark with s squared, it is better to know about s itself. Because if I know what is that number for s, then I can square it, yes? So this means that this will motivate me to answer this question now. Do you agree? If I can answer this question, that is a matter of squaring both sides. Okay, but how can I answer that one? This is a sum. So I need to do them one by one. So let us just write some of them. So S is this number that I am writing. And let me write some of the terms in front of our eyes. And then I continue. And then I want to simplify this sum in module 10. Okay. So, what is a good name for 1 when it comes to module 1? So module 10. 1 itself, yes? Plus, what is a good name for 2 factorial when it comes to module 10? 2 itself. What is a good name for 3 factorial when it comes to 10? 6. What is a good name for 4 factorial when it comes to module 10? You need to remember, what is 4 factorial as a number? What is the value for 4 factorial? 1 times 2 times 3 times 4, which is 24.
Yes.
But 24 went beyond my module. When it goes beyond my module, I can reduce it. So what is the correct number for 24 in module 10? 4. So this means that instead of 4 factorial, I write 4. Okay, but that's the point. You might say, okay, this is a boring exercise, I have to continue. But now this process will stop, and then you can say that from now on, this is the number. Can you see that? For example, what is 5 factorial? 5 factorial means 5 times 3 times 2 times, 5 times 4 times 3 times 2 times 1. Can you see what is this number in module 10 immediately? Yes? 0, because 5 times 10, 5 times 2 is 10, it's a multiple of 10. So the multiple of 10 in module 10 is 0. But what do you think about 6 factorial? It's also 0, because when 5 factorial is 0, 6 factorial is 6 times 5 factorial, yes? So if I ask you, what is this number module 10? You will tell me it is 6 times 5 factorial, as usual. But you just answered this part. So this is just in module 10. This is 6, of course. But 5 factorial in module 10 is 0. So this becomes 0. Okay? In a simpler language, when 5 factorial is divisible by 10, isn't it clear that every number after that is also divisible by 10, because we're multiplying them. So I will get a bunch of zeros after that. So all of them are individually 0 in module 10. So it was not that hard, yes? And then I add them up. These are simple to add. So 1 plus 2 plus 6 is plus 4. How much is that? Is 13. But 13 isn't, even though it is correct, but it cannot play the role of the units digit. So what is this units digit? 3. So we answered this question, Mark. We learned that S is congruent to 3 modulo 10, and then I want to answer my question mark. So this motivates me to raise both to power 2. So this becomes S to the power of 2 is 9 modulo 10. And I don't need to simplify 9 more because 9 is acceptable. So this means the answer to the question is 9. So if you calculate S, square it, if we haven't done something wrong, the units digit of that number that we get is what? Is 9. By the way, it's a good idea to see if we can check this using GeoGebra. It's good to know. So we start with sum. I don't know if there is... okay, I have this keyboard here. Okay, I write the sum, and you want to write 1 factorial plus 2 factorial plus 3 factorial up to 19 factorial. You can, of course, write them one by one, but using this instruction sum, I can write k factorial. I hope that there is a factorial sign. I think exclamation mark works fine, yes. So just exclamation mark. And then I want to sum k factorial, but k goes from where? This is the format that you need to write. K factorial are my terms. My counter is k, but k starts from 1 and up to 19. Yes? Okay, so it calculated that.
You put 9, not 19.
Oh, sorry. Okay, 90. Oh, that's a bit much bigger. So so if that's correct, we made a mistake. Yes.
We have to square it, don't you?
No, but if when it ends with 0, square it also ends with 0. Unless I am making mistake in the syntax of GeoGebra, but I'm sure that this is calculating the wrong thing. So let me calculate. For example, 5 factorial might be exclamation mark. Yeah, that's correct. 1 factorial, 2 factorial, up to 9 factorial. So I have it on the board. The units digit should be 3. To be honest, I don't understand why. Let me see. No, I haven't done something wrong. Let me just type it once more. So when I say sum, I use this syntax, and okay, I have to use this one. Expression, variable, start value, end value. So what I have done is right. Expression is, so if you don't, yes, I would say k, and then I factorial. And my variable is, of course, k. My starting value is 1. My end value is 19. Then I don't know it's insisting that this is correct. I should bet on that it is not correct.
Hold back.
Yes?
Shouldn't you put the start value as 1 factorial and the end value as 19 factorial?
No, because I put the factorial there.
You can try.
No, it doesn't work. Why should I try? Because it is quite k factorial. The factorial sign is here. Okay, so let me try to see if Wolfram alpha answers me somehow.
Expression is okay factorial.
Can you see some flaw there? Is that right? So yes, I don't know. Let me just calculate this using this one. So GeoGebra has the wrong answer.
Can you compare
So our calculation is correct. So you see, at least it ends with a 3, and I don't know, it's a very serious bug. I think more or less everything was right. I don't remember, but this number looks familiar from GeoGebra.
Can you check and compare?
Yes. Let me just see if I can copy this or not.
It says plain text down.
Ah, yes, this one. So, okay, it copies everything, but anyway, it's good. So I will go here in GeoGebra and try to Control V. It doesn't work here. Okay, but anyway, yes, I mean the first few digits seems to be right, but for some strange reason. So it means that calculation by hand is sometimes better than using computers, but that is a very... No, but this doesn't reach the decimal point. If you want, I can also check that, because this is the number of decimals. Might be these numbers are smaller. Yes, that's a good idea. Yes, this setting, how many digits are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So 19, but let me see, do you know where is the setting? No, round up to 2 decimal points. I mean, it is very strange. If you want, I can change it to, it doesn't have it even more than that. No, I think there is something wrong with it.
Can you turn off?
I don't know why, but this is a very straightforward calculation, so it's not very complicated at all. Okay, so if we go back to Wolfram alpha, for some reason, you see this is the correct answer, and I hope that you agree that even if I square it, the answer becomes 9, because I don't care how big this number is. When I square it, the units digit is definitely squared, and it gives me 9, so that's correct. Anyway, okay. So what we do, okay, so I don't know, because this is a very strange, because this is just adding some numbers and GeoGebra makes it wrong. So this Wolfram alpha shows that our answer on the board is correct. So that is very good. In the exam, you cannot rely on GeoGebra, okay? So you have to calculate it yourself. Okay, so I write one more question here. My question is that, can you write this product as with using factorial signs or whatever you want to? I just multiply the even numbers. So I multiply 2 by 4, by 6, by 8, and then I continue until I reach to 2 times n. Okay? So my point is, can you write this using factorial sign? Because this is not 2n factorial, yes? Because 2n factorial also includes the odd numbers. But I'm just asking, can you rewrite the same expression without these dots? Okay? So I want you to use the factorial symbol somehow to write this without these dots. So how do you think I will solve the problem? Yes?
If you factor out the 2, then you get 2 times 1 times 2 times 3 times 4 up to n, then it's 2 times n factorial.
Your idea is correct, but you made a minor mistake. This is not factoring out 2, because 2 is involved in each one of these factors. Yes? So factoring is like this. If you have 2 plus 4 plus 6 up to plus 2n, your idea is right. You factor 2 out. And then what is left is 1 plus 2 plus 3 plus up to n. But here I do not have the sum, I have the product. But your idea is correct.
With 2 to the n times n.
Yes. So every one of these terms includes a factor of 2. Yes. So this is the idea. So the idea is this. Instead of this first 2, you can imagine in your head 2 times 1. Instead of 4, you can imagine it as 2 times 2. And instead of 6, you can imagine 2 times 3. And for 8, you imagine 2 times 4. And of course, up to the very end, it is already written as 2 times n. So if you multiply all these things, order doesn't matter, yes? So what I do, I have a 2 here, a 2 here, a 2 here. In each one of them, I have a 2. How many 2's I have? I have n terms, so I have 2 to the power of n. Yes? But then what is left from here is 1. What is left from here is 2. I haven't considered yet. I haven't considered 3. I haven't considered 4. And I haven't considered n. But that's also something I know, because that's a product of integers from 1 to up to n. What I can write here is n factorial. So this product can also be written as factorial. Okay, let's make it a little more challenging. What if I multiply the odd numbers? Yes, so what I do, I start from 1 and then multiply it by 3, multiply it by 5, multiply it by 7, and I continue until I reach to the nth one, 2n minus 1. So if I insist to write this expression without those dots, you have to use a factorial notation, but it is not as simple as that one, but it is not hard, by the way. So how should I do that? The idea we had in the very beginning, do you remember I told you to write 10 times 9 times 8 using factorial? You remember how I solved the problem in the very beginning of today's session? So how should I do that? How did I solve that one? Multiply and divide. That's the same idea here. So what, multiplying by what and dividing by what? Yes? Exactly. So you multiply by the product of even numbers and then divide the product by even numbers. So in other words, I write this, instead of writing it, I can write it 1 times 2 times 4 times 5 times 6 times 7, and I continue times 2n minus 2 and then 2n minus 1. Yes? Of course these two are not the same, but I can compensate for the change. What I did, I multiplied an extra 2, so I missed 3, yes, sorry. I multiplied a 2, I multiplied a 4, I multiplied a 6, and I also continue to multiply 2n minus 2. But to compensate for the change that I made, I divide by everything that I multiplied. So it means that I divide by a 2, I divide by a 4, I divide by 6, and I divide also by 2n minus 2. Is that right? Okay, but the numerator, if I ask you to write in the factorial form, what's the answer? The numerator is the product starting from 1 going up to 2n minus 1, 1 by 1. So instead of numerator, I can write 2n minus 1 factorial. Yes? But in the denominator, that's the same problem. The only difference is that I have 1 step less. Yes? So can you tell me what the answer is? Here I have the product of only even numbers. I can do it exactly like this. The only difference is that I have 1 term less than the previous case. The previous case is stopped at 2n. Here I am stopping 1 step before. Yes? So what should I write here in the denominator?
2n minus 2 factorial.
No, 2n is not the case, because how many factors are there? n minus 1.
Is it 2n minus 1 factorial times 2n?
2n to the power of n minus 1, yes, multiplied by? Multiplied by n minus 1 factorial. Yes, I have one term less, yes? Is that clear? Okay, so these are ideas of this. So I hope that you'll actually get familiar with this idea of factorial, okay? Next time we will start exactly according to the book. So the next time I will talk about permutations, yeah? So I cannot add some pages in the book yet, but I will do that later. Any questions? Thank you.